So let's continue. So the exercise that I have here is one of those exercises that if you don't know what's happening, or if you don't have like all the tricks in hands, you are going to get mad at Alex, because this exercise is very tricky, and you will see a few ones like this one, and you will see why. All right. So we are going to start working with it normally, and on those step or those situations where you need to know what's happening, or when you need to know specific information, I will going to stop and I'm going to tell you what to do in those situations. All right. Okay. So I will try to zoom in on everything that I write here. The first thing I want to write is just the function. The function is going to be okay. So this is the final answer. Let me move the final answer. Just I'm going to put it here. We are going to get back to the final answer, well, at the end. All right. So here is our rational function. And the first thing that we want to try to do is to simplify. Right? But this is not always going to be always possible to do. Let's try to simplify this to see what happens. All right. Looking at the denominator, we can see that there is no common factor within the two terms, so there's nothing that we can do there. And then the numerator, we have a quadratic equation in standard form with a big flag here, a big problem here, a big no-no is that the leading coefficient is not 1. Okay. I think in the majority of the cases when the leading coefficient is not equal to 1 in a quadratic equation, it won't be possible doing the FOIL factorization or find the factorization of the quadratic equation by the method that we know. So you are seeing already this leading coefficient here. So that is going to flag you. That's going to be a flag. Well, this might not be possible to factor. And that's the thing. That's going to happen. That is the case for this exercise. That here you want to find two linear factors for the numerator. And it won't be possible. Alright? So basically, try to simplify. You just start seeing weird stuff. That means that it won't be possible to simplify the function, right? So there's no way we can simplify this function. What can we get from this first step? Well, we can get that there's not going to be any holes on the graph. Okay. From the first step, if we are unable to simplify the function, it means that there is no hole in the graph. Next step, it would be to identify the domain. We take the denominator, not equal to 0, and we solve. Not equal to -1, and then x can't be equal to -1/2. All right. There's no simplified version, so we know that this restriction is a vertical asymptote. There is no hole in the graph. Okay, step number 3 is to find any vertical asymptote or any holes. We know that there is no holes because there is no simplified version, so the only thing that we have here is the vertical asymptote at x equals -1/2. All right. Step number 4, oblique asymptote or horizontal oblique asymptote. So start HA, horizontal asymptote or oblique asymptote. Okay. Okay, and I want you to tell me what kind of asymptote we have here. Do we have an horizontal asymptote or an oblique asymptote? Okay. What type of asymptote we have here? So Rachel, you are saying that we have horizontal asymptote. Do I have any other do I have any other suggestion here or answers from you? Horizontal asymptote or oblique asymptote? Amanda, Cassandra, Tristan, what do you think? Okay, let's review the cases. Numerator degree is 2, okay? Amanda, vertical is only when we are working with the restrictions. So we have a vertical asymptote of x equal -1/2, but now we are trying to identify any horizontal oblique asymptote. Okay, so I have here, Tristan says oblique asymptote, that's correct, and then Rachel says the numerator is 2. Then I believe you are referring to the degree. The degree of the numerator of is 2, that's correct, and the degree of the denominator is 1. Okay, and because the degree of the numerator, which is 2, is 1 degree greater than the degree of the denominator, we have an oblique asymptote. Okay, so in this case we have an oblique asymptote. So we have an oblique asymptote, and we know that the equation of the oblique asymptote is going to be a linear equation. How are we going to get that equation? Now we need to do long division. We can do synthetic division here, but since the leading coefficient of the denominator is not 1, it might complicate things. So here we are going to do long division. Okay. Why are we going to do long division? Because the quotient, the result that we get from this division, is going to be the oblique asymptote equation. Okay, see, because we are going to divide a degree of 2 by a degree of 1. So what's happening with the quotient? The quotient is going to be a depressed equation, 1 degree less. All right. So in this case, the quotient is going to be a degree of 1 polynomial, So that is going to be the linear equation of the oblique asymptote. How do we do this? Anyone who needs help or still who needs help on doing long division? Do you feel comfortable doing long division? Let me know that in chat. Okay. All right. So let me use colors to show you what I do or the steps. Okay. So we are going to be, how many terms we have here? So we have 3 terms. So we are going to be working one term at a time. Okay. So the first thing that we are using here is 4x squared. Okay. What are we going to do with that? We are going to take 4x squared and we are going to divide it by the leading term of the polynomial that is outside, by the divisor, by 2x. So you are going to do that division. All right. This is step number 1. And from here, you are getting 2x. Okay, so this result goes on top, on the top, and what you want to do here is to align 2x with the like terms here. So with the like term that we have from the polynomial that we have here on inside the rectangle or the house of the division. So the first term here is a degree of 2, or half x powered squared, or x squared, right? So that is the first term, right? The second one has a degree of 1, 2x. So you want to put this result 2x here, 2x. So you align whatever you have on the top with the terms at the bottom. Okay, if you put 2x here, it's not going to be wrong, but it's not going to help you to know when you are finished with the division. So that's step number 1, right? Now, what are you going to do? You are going to take this number and you are going to multiply by the entire divisor. Divisor is the polynomial that is outside. Okay? So that's what we are going to do. 2 times x times 2x plus 1. That is going to give you 2x squared, is 4. 4x squared, right? Plus 2x. Okay? And this result goes here. Okay? See that my terms are aligned. The degree of 2 with the degree of 2, and the degree of 1 with the degree of 1. Okay? Now we are going to subtract. Okay? So remember that we are working with the first term here in the dividend is the polynomial that is inside the house of the division. Okay, so what's gonna happen if we are doing this correct? This result, this first term, are going to cancel each other. Okay, and this is one way to know that we are doing it right. Okay, the next term give off 10x. All right. Okay, so at this point, we have finished with using the first term of the divisor. So this one, we are finished with that one. Now we focus on the second term, but we focus on 10x. Okay. Also, you want to bring down +1. Okay, you want to bring down +1. So we are going to repeat this process where we take the leading coefficient, the leading term, and we divide the leading term of the dividend by the leading term of the divisor, which is 2x, and then the quotient of that division, we multiply that quotient by the entire divisor. Okay. So let me simplify this. I'm going to erase all this. Okay. I'm going to erase this 0 because there is not need. Okay. I'm going to erase this arrow because now we want to focus on this 10x. Right? So now 10x divided by 2x. Okay, 10x divided by 2x. This is 5. The quotient of 5, see that is constant, so it is aligned with the constant part here. Okay, and then we have 5 here. The next thing that you want to do is to multiply 5 by the entire divisor. But since we want just the quotient, what we got on the top is the quotient, we can't stop there. And how do we know that we are finished with identifying the quotient? Because we have reached the constant term here. Okay, that's why I like to align the quotient with the dividend. Because once we reach the constant term, we know that we have finished with the quotient of the division. Okay. The other thing that you want to get is the remainder, but for this exercise, the remainder is not important. Yet you want to verify that your value is correct. So you are going to multiply 5 times the divisor, right? So 5 times 2x, that gives us 10x, and then 5 times 1, that's 5. Then we want to subtract to get this 0. This 0 here is the one that's important because that 0 is going to tell us that we have done correct our work, right? Give me just a moment. All right, I'm back. Okay. So that's how we do long division. And what we want to take from the long division is the quotient. So this linear equation that we have here. So the oblique equation is 2x plus 5, right? So that's number 4. Any questions so far? All right, intercepts. All right. So let's start with the x-intercepts. And you remember that there is a shortcut where if we are looking for the x-intercept, we just need to focus on the numerator. here is our numerator. So our main goal to get the intercepts is to get key points. Okay, those x-intercepts are going to be key points for us. If the exercise is not asking you for presenting the intercepts, you might want to skip this step. And why do you want to do that? If you are going to solve this equation, we know that we cannot use the factorization because right now we don't have the methods to do the factorization of this polynomial, okay, other than just finding the zeros, okay, finding the zeros and then the linear factors, right? So in order to solve this equation, we need to use the quadratic equation. Okay, so we have here the quadratic equation. Okay, and I'm going to solve it. So we have 144, and then here we have 16, and here this one is 4. Yeah, this one is 4. And here is 8. So this is 128, and this is 8. Okay, at this point, you want to stop there. Why? It's because the exercise is not asking us for finding the x-intercepts. This is not going to help us to ask for a key point, because look the writing of these two values. Okay, there is a square root that is not perfect, so that means that value contains a square root there, an addition or subtraction by a square root. We cannot simplify these two values representation further. Okay, so it's going to be a very uncomfortable value to work in the coordinate plane. So here you want to stop. You want to say, okay, the exercise is not asking me for the x-intercepts. I'm not going to use the x-intercept as my key points, because it is going to be very difficult to identify that value. Yes, you can use your calculator and get the decimal representation. That's completely okay. But even though with the decimal representation, you don't want to use uncomfortable or complicate values in the coordinate plane. You want to find the easiest or the more simple values in the coordinate plane, so it will be easier for you to represent the graph of that of the function, right? So here you stop. Okay, you are seeing that these values are going to be not complicated but uncomfortable to work with them. So skip the x-intercepts. Let's see what we got from the y-intercept. Let's see, we have more luck with the y-intercepts. So my equation is here. So we know that whenever we are looking for the y-intercepts, the x value is equal to 0. So the y-intercept just is a value that you want to use, because this is going to give us 1 over 1. Hence the y-intercept is 0, positive 1. Okay, so this one is a point that you want to use. Okay, these 2 points that you're getting here, no, you don't want to use them. All right, so now we are ready to find the key points. So far, we have just one point, which is the y-intercept. We know that we are going to find to the left side and to the right side because we have just one vertical asymptote. The vertical asymptote is x equal negative 1/2. So the y-intercept, it is located on the right side because 0 is greater than negative 1/2. So for the left side, I'm going to use negative 1, and I'm going to use negative 2. And for the right side, I will need to use one more, so I'm going to use positive 1. Okay? So when using 1, let me copy the graph, the function. Seriously? Okay. So using 1 there, I think I can copy this. Negative 1 in this case. So with negative 1, I have 4 here, I have negative 12, I have 1, then I have negative 2, and negative 1 here. So this is going to give me negative 8, negative 7, positive 7. Okay, so that point is negative 1, positive 7. Okay, so 4 minus 12 is negative 8, plus 1 is negative 7. All that over negative 1 is positive 7. So okay, so we have negative 2 square, that's positive 4 times 4, 16. Then we have negative 24 plus 1. And here below we have negative 4 plus 1, that's negative 3. From here we have negative 8 plus 1, negative 7. Over 3, so 7/3. So here, negative 2, 7/3. Okay. Even using negative 2, I have a y value of a fraction. It's not an ideal value for the y value, but it's better than using a number with a square root there. So those are the 2 points on the left side. Then for the right side, I think I will get 12 plus 4, 16 plus 1 is 17, and then over 3. So 117 over 3. Okay. So my 4 points are -1, 7, -2, 7/3, 1, 17 over 3, and 0 and 1. Okay. I'm not going to draw this graph because it's going to be impossible for me to do this. Okay, not because it's something way beyond difficult, it's because I can draw with this thing. Okay, but what you are going to do on Alex is you are going to plot the points, you're going to plot the vertical asymptote, the oblique asymptote, and then you are going to get the right answer. So you are seeing here the right answer. One thing though, to identify the oblique asymptote is here, which is 2x plus 5. Treat the oblique asymptote as a line because it's a line. So that means that for the oblique asymptote you need to have 2 key points. Okay, so those key points are going to be when x is equal 0, y is equal 5. So that is going to give you 1 point of the linear of the oblique asymptote, and then with x equal 1 and the y value is 7. So with those 2 points, now you can use that function of the oblique asymptote. So then you can draw a line, attach a line with dashes, okay, representing the oblique asymptote. Okay, so yes, you want to find 2 more points, but those points are for the oblique asymptote. And then you plot the points and connect. Plot the points and then connect. Okay. Also, you need to use this function, this tool, to do the vertical asymptote. Okay. Any question on this one? All right. All right, so now we are in the other way. We have the graph. Now we need to construct or build up the equation of the graph. So this is how you will see this exercise. You have the graph. Then you need to choose first the structure of the function equation of the function, and then you need to find the values for each constant a, b, and c, or d. You have the graph of the rational function, and you have some information. Okay. The first thing that we have is that there are vertical asymptotes. Those vertical asymptotes are located at -1 and 6. So here we are seeing 2 vertical asymptotes, and those 2 vertical asymptotes are -1 and -6, +6, sorry. Okay, what can we get from just that information, that piece of information? We can get that these 2 from the vertical asymptote, we can get that there are 2 linear factors in the denominator. Okay, and how are we going to use that information? Well, we know that we need to select the structure of the function. And in the first choice, we have just one linear factor. That means that this structure is not. In the second one, we have another option with just one linear factor in the denominator. So this is not the choice that we want to choose. So here we have 1, 2, 1, 2, and 1, 2. So the correct choice will be on either of these three, all right? But then we need more information because now we need to determine which of the three is. Horizontal asymptote y equals 0. What can you get from that? Okay. If I told you the horizontal asymptote is y equals 0, what can you say about the degree of the numerator and the degree of the denominator? What can we say about them? Okay. And you need to go back to the cases. When do you have a horizontal asymptote, on which case you have a horizontal asymptote with y equals 0? In which scenario is that? What is the relationship here between the degree of the numerator and the degree of the numerator? Okay, tell me your answer on the chat. Amanda, I have degree of the denominator plus degree of the numerator is equal. Equal? Amanda, is the degree of the numerator has to be less than the degree of the denominator because y is equal to 0. Let's review back the cases. Case number 1, horizontal asymptote, y equals 0, degree of the numerator is less than degree of the denominator. Okay, when they are equal, then the horizontal asymptote, it will be the value, it will be the leading coefficient of the numerator over the leading coefficient of the denominator. So y equals 0, here is important, key concept, is that tell us that the degree of the numerator needs to be less than the degree of the denominator. Degree numerator less than degree of denominator. Okay. Okay. So from that piece of information, now we are going to check if we need to cancel one of these three, or two, or maybe the three one. Okay, from the first one, this one that we have here, we are seeing that the numerator is a constant. It's just a, there's no variable here. And because here we have two linear factors and the multiplicity of each factor is 1, so the degree of the denominator here is 2 and the degree of the numerator here is 0. So this one is good. Here we have one linear factor on the numerator and two linear factors on the denominator. All of these factors with multiplicity of 1. So that means that the degree of the numerator is 1, degree of the denominator is 2. So it is less. Degree of numerator is less than degree of denominator. So this one is also good. Then on the third one, we have two linear factors on the numerator, two linear factors on the denominator, all of them with degree of 1. This one is not, because here we have equal degree between numerator and degree, numerator and denominator. Okay, so the battle is between these two. The graph does not have x-intercepts. The graph does not have x-intercept. What can we get from that information? The graph does not have x-intercepts. Remember the shortcut when we are looking for the x-intercepts. We just need to focus on the numerator. If the numerator does not have an x variable, it means that the graph or the function does not have an x-intercept. So the meaning of the graph not having an x-intercept means that the numerator needs to be constant. Okay, so the numerator needs to be constant. Here, in this one, we have a variable of x in this structure, but the graph does not have an x-intercept, so it cannot be this one. The structure that we are looking for is the one that we have here, because there is no x-intercept. It means that the numerator is a constant value. Okay, so we know now we know the structure. So far, we know the value. We know the value of B and C because we have two vertical asymptotes. From the vertical asymptote, we can get -1 as one zero of the denominator and positive C as another zero of the denominator. So if those are zero of the denominator, we can bring those into linear factor of the denominator. So x plus 1 and times x minus 6. Okay? So the only thing that is missing is the value of a. So let me if I can I get this? Nope. Nope. Okay. So let me write what we have so far. This is what we have so far, and we still need to find the value for a. What else do we have here? We have that the graph passes through the point 0, 1. So it means that we have 1 point, 0 and 1, 0, 1. Okay, that's the point, 0, 1. This point is our y-intercept, but that's not important here. What is important here is that now we can substitute 1 as the value for the function, and we can substitute all x values with 0. Okay, we still have a here. We need to find the value for a, but now we have an equation with only one unknown variable. So a, we can solve for a. And this is a, not 9. So 1 times -6. So this is all -6. Multiplying both sides by -6, we got the -6 on the left side is equal to a. So our answer, it is f of x equals -6 over x plus 1, x minus 6. Okay? And that's how you solve that one. And for this one, there's the written words that you need to show for this one is that one. Okay? We have one more. Okay? And here, in this exercise, what do you want to do? I think we did something very similar to this one. You want to use the properties that you can get from here to find the correct answer. For example, let me start with let me just do f of x. We have 2 over x squared plus 2x minus 3. All right, so the first thing that I will want to do here is, because we have all these graphs have two vertical asymptotes, so I want to find the restriction of f of x so I can identify which are the correct asymptote for f of x. So I take the denominator not equal to 0. I do factorization because I have a leading coefficient of 1, then plus 3 minus 1 means that x can't be negative 3, x can't be positive 1. Okay, I know that there's not going to be holes in the graph because there's no way I can simplify further f of x. So now I will go and identify which of these graphs have a vertical asymptote at negative 3 and positive 1. So A is 1, this one is negative 4 and positive 4, so B is not the graph of f, neither C. Here I have 3 and 1, so it could be B, it could be A, it could be D. E is also a possibility, negative 3 and positive 1. F is not the graph of f. All right, so we have just shortened the options to A, D, and E. All right, so what else do we want? Because the numerator is a constant value, so it's 2, there is no x variable in the numerator, I know that the f does not have x intercepts. E has 2 x intercepts, so E is not the graph of f. D has 1 x intercept here, so D is not the graph of f. So the right answer for f is graph A, because there is no x intercepts and we have vertical asymptote in negative 3 and positive 1. Okay, so that's how you want to answer these questions. With the properties that you can get from the function, you will identify the correct graph. Okay, you will do the same for g of x. All right, so those are the exercises. Unit number 7, and I wanted to go over. What is left before going through your question ratio? Anyone that have a question? Anyone have a question about what we just discussed today? Okay. For these exercises, where you need to draw the graph of the rational function, this is the written work. This one is a lot of work, but this is all the written work that you need to do for graphing the rational function. Yes, Richard, I can email you the answer. That's okay. Okay. All right. Well, if there's no questions, Richard, I'm going to be working with your question. I'm going to send you an email. Yeah, I wish you a great rest of the day and the week. What do we have next class? Okay, yeah, I will see you on Monday. On Monday, we are going to discuss unit number 8 and number 9, and then you are going to be ready for quiz number 4. Okay, thank you, everyone. Have a good day, and let me know if you have any questions. Send me an email. You know, I always be happy to help you. Bye-bye.